we will be starting with our next unit, which is on interference pattern, or in general the phenomena of interference. Before I begin, I would like to mention that I have used certain images in this PowerPoint presentation, and those images I have taken from internet, and I have included the original link of the websites from where I have taken the images. So kindly refer to the original source in case you want to reuse those images. The copyright belongs to the original authors. Well, so let us now start with the topic of interference. And in this topic, we will be covering the following components. I will first give you a quick overview of what are waves, the traveling waves, and what are light waves. Then we will be talking about electromagnetic spectrum in brief. What is electromagnetic spectrum? What all types of waves exist in electromagnetic spectrum? And then we will be talking about waves and the concept of wavefront, means how the waves originate from different sources and how they propagate in space, and what kind of wavefronts different sources of waves can lead to. Then we will be talking about plane and spherical waves. What are plane waves and spherical waves? How the two are different. Then I will be talking about this theoretical overview of the interference, that what is interference in general, and how we can mathematically describe the interference of two light waves, two or even more light waves. And then we will be talking about the fringes obtained as a result of interference of two monochromatic light waves, and rather two plane waves. So let us begin. We have already studied what are traveling waves. I hope you remember from your previous classes, a topic in which we had discussed how we can write down wave function for a traveling wave. So the wave function for a traveling wave looks like this, where this A is the amplitude corresponding to that wave function, and then this kx minus omega t. Basically, we had there done that a function of type, say, f of x minus vt represents a wave traveling along positive x direction. I hope you remember that. Now here, this particular form makes sure that we are representing a traveling wave, and that the characteristics of that traveling wave are sitting in k and omega. A here is the amplitude. So basically, wave function may be representing variation of a certain physical quantity. For example, in a wave traveling in a string, it is the y displacement of the string from its otherwise horizontal position. In sound waves, it may be a variation of pressure at different points in the space for different instants of time. So basically, in a wave, in a traveling wave or a propagating wave, there are two components. One component is space variation, space period. There are two periodicities actually. One is a space periodicity, which is sitting here in the form of kx. Another one is temporal periodicity or time dependent periodicity, which is sitting here in the form of omega into t, right? So k, the space periodicity, is characterized with the help of a number which we call wavelength, and the wavelength is related to this k with this expression. So k vector, this is called wave vector, is equal to 2 pi by lambda, and this is a vector quantity. So its direction is along the direction of propagation of the wave. Now omega is related to time period or periodicity, temporal periodicity of the oscillation of the particles of the medium by which the wave is propagating. So this is actually temporal periodicity of the wave function, we would say. So temporal periodicity of the wave function is related to omega. We have done it in detail, so I'm not going into much detail here. So omega is related to nu, the frequency, with this expression. So omega is equal to 2 pi nu. So that is fine. And if we want to know how the wave travel in the space, or what is the velocity of the wave, we know this well-known expression, v is equal to omega upon k. So if we know the wave function in this form, we can tell what is the wavelength of the wave which is traveling, what is the frequency of the wave which is traveling, and what is the velocity with which this wave will be traveling. Now light waves. How is this light wave to be described mathematically? So basically, we all, I think, have done in our lower classes. I'm not sure if you have done a course on electrodynamics, but still in our lower classes we have done that the light waves are nothing but the electromagnetic waves. Means those are the waves which are created by uh, time varying electric fields, and those time varying electric fields gives rise to space varying magnetic fields, and vice versa. And that is why the intermingling of those varying electric and magnetic fields leads to the electromagnetic waves traveling in the space. So what is the wave function for light waves or electromagnetic waves? This is, we can choose the variation of electric field at a certain point in the space, and at certain instant of time. So we can write down the wave function for say light waves or electromagnetic waves according to say this given form, where a is the amplitude, and omega is the same temporal frequency, you can say, or it is something which is related to time dependent periodicity associated with the waves, and this is k, which is the wave vector. So in case of light waves, the expressions are similar. There is one thing which is worth highlighting. If I this first portion is the simple expression of lambda. This is lambda is equal to v upon nu, where v is the velocity. So it is just simple. V is equal to nu into lambda. So this is the same thing. Nothing. I mean, here we have just written nu in terms of omega. So nu is equal to omega upon 2 pi. So this is what we have substituted here. Main thing to notice here is that, okay, the velocity of light waves is c in vacuum, means it is velocity of light 3 into 10 to the power 8 meter per second. But whenever those light waves travel in the medium, some different mediums, then this velocity of the wave can change. So v, if is the velocity of the wave actually, then v can be replaced in terms of c, the velocity of light in vacuum, divided by n, the index of refraction of that medium. So you know that basic defining definition of refractive index. So that is why v is equal to c upon n into nu. So that is how wavelength lambda of a same light wave can be different in different media. Means space periodicity can be different in different media. Anyway, let us now talk of say this is in general representing a light wave traveling in any direction in the space, say r. It has all three components, x, y and z. Now if we want to represent light wave traveling along say z direction, what is going to be the expression? Try to guess it in your mind, write in your notebook. So that is going to be like this. Here we have to just replace r with z. So this is representing light wave traveling along z direction. Now I give it to you as a thought assignment that is this in which direction this light wave is traveling. Means is it traveling along positive z direction or negative z direction? So pay attention to this minus sign here and then accordingly answer the question. Now, okay, let's come back here. The frequency for a wave can take different values, and depending upon the value of this frequency and of course the value of the wavelength, mainly it is frequency here, because wavelength depends upon in which medium the light is traveling, so it is not absolute quantity. So it is the frequency which is more crucial here. So depending upon the frequency of oscillation of electric field, the electromagnetic waves can be divided into different regions, and that whole uh, uh, region or whole range of variation of frequency is called electromagnetic spectrum. So basically, this electromagnetic this is a graph which I have taken from this website, and this was a very interesting, very good graph. So let us first talk of the electromagnetic waves in the different regions. So the electromagnetic waves whose wavelengths are of the order of say kilometers. So you can see this is the range of the wavelength in meters. So 10 to the 3 meter. So the radio waves can have wavelengths as high as a kilometer. Means the typical size. This is just approximate scale of the wavelength. So the wavelength of radio waves is of the order of the size of buildings you would see around. So radio waves are, you can say, very large wavelength waves, and wavelength and frequency are inversely proportional, so they are having frequency which is very very less, say 10 to the power 4 hertz. So how does frequency relate? So you can take product of wavelength into frequency and put it to be equal to c, the velocity of light, this which is 3 into 10 to the power 8 meter per second, and then from there you can find out how these two numbers are to be related. So wavelength, if it is 10 to the power 3, you put lambda in say that equation, means nu lambda is equal to c, and then you can find out frequency, and that would be of this order. This is just order, and this figure tells you, okay, what is the typical temperature of a body by virtue of which body can be emitting the radiations of this particular wavelength. So this you should relate to phenomena which you have studied in your lower classes, and say this is known as black body radiation. Means every body, if it is at finite temperature, it emits certain radiations. So this scale tells you, okay, what should be the typical temperature of a body at which it would emit the radiation of this specific wavelength or frequency as having maximum intensity, because in black body radiation, energy emitted by a body at a high temperature, it is not belonging to a specific wavelength, but this tells you what is the wavelength with maximum intensity which is emitted at that particular temperature. Anyway, we are not going into details of that. We just want to get a quick overview of what is electromagnetic spectrum and what all it covers. So this part here takes care of whether these waves can travel through Earth's atmosphere or not. So if you come here, you would see that okay, depending upon the wavelength, we have radio waves, we have microwaves, we have infrared waves, visible rays, our the light or optics, which conventionally was known as, that originally came from this light, so visible spectrum, and then ultraviolet, where the frequency is still higher. Then you have X-rays, then you have gamma rays, and this tells you the typical order of the wavelength. What is the order of the wavelength? So you should see that X-rays are of the order of size of an atom, and this you can also try to relate roughly to the size of the source from which such kind of radiations may be emitted. So say for example gamma rays, their wavelength is typically of the order of 10 to the minus 12 meter, which is size of atomic nucleus, and then we know that those gamma rays are emitted by atomic nucleus. So just a rough estimate. Okay, so that's your whole electromagnetic spectrum. You should see that all those waves are not, or they cannot travel through our atmosphere. And there are certain region of there is certain region of electromagnetic spectrum which can travel through our atmosphere. So that is why, since a visible region can travel through Earth's atmosphere, we are able to receive the light coming from the sun. And then infrared, this gray area means they can partially travel through the atmosphere, partially they are absorbed. Microwaves are not they cannot travel through atmosphere, and similarly with the other waves. So this is just quick overview of electromagnetic spectrum. So means the omega frequency which is appearing here, this yeah, this frequency appearing here, based upon what is the value of this frequency of electric field or oscillation of the electric field, we have a broad electromagnetic spectrum. And each spectrum has its own special relevance. In itself, it is a field. So for example, if you talk of microwaves, then these waves can be used for heating in your homes. These can be used for mobile communication. Radio waves, you would have heard of radios, and then typical megahertz region. So radio waves can be used for communication. So this is how various regions of electromagnetic spectrum are important. This is again a quick overview of response of Earth's atmosphere to the electromagnetic spectrum. You would see here is our so this graph is reverse of the previous one. Reverse means, okay, here well, when we go from left to right, the wavelength is decreasing, right? And here in this graph, when we go from left to right, the wavelength is increasing. So make sure it is opposite of the previous slide. So here it is showing opacity of atmosphere to electromagnetic radiation. Now, as we have seen here that, okay, most of this region of electromagnetic spectrum is not allowed to pass through our atmosphere. The same thing is shown here. So this belongs to that region. So our atmosphere is opaque to this whole portion of the electromagnetic spectrum, and that is why we are saved from those harmful ultraviolet radiations coming from sun. And that is why, since our atmosphere is opaque to those ultraviolet radiations, it doesn't reach to Earth at Earth's surface, and we are saved from that. Otherwise, those are very harmful for our body or human skin. Anyway, and you will see here that this visible spectrum opacity, for this visible spectrum, opacity of Earth's atmosphere is very low. Means it is very transparent. If something is not opaque, means it is transparent. So means we can say Earth's atmosphere is very much transparent to this electromagnetic spectrum, and that is how we can very easily see the light coming from the sun, all the colors. So this is Vibgyor, so that is why we see all the colors. This was that gray area. This is referring to that gray area. So the opacity for different wavelengths is different, and this gray area actually depends on the constituents of the atmosphere. So I mean, what are the molecules in the atmosphere? Some of the wavelengths are absorbed by the water molecule, some of the wavelengths are absorbed by the aerosol particles, and so on. So that's it. This part characterizes this. This in itself is a very vast area, and comes under radio and atmospheric sciences. So we won't be doing that in detail. We just want to know, okay, in quickly, that okay, how does electromagnetic spectrum what is electromagnetic spectrum, and how our atmosphere behaves to the electromagnetic spectrum. So here is the radio waves. You should see here. Radio waves means our Earth's atmosphere is opaque to those radio waves. So for all our satellite communication, radio waves are perfect one, because if we have to communicate to extraterrestrial bodies, then the signal which we are sending from Earth must not be absorbed by our atmosphere, and it is found that radio waves are very suitable for this purpose. And Now I put you a question to you. We have discussed that, okay, microwaves are, if you come here, okay, the microwaves are not allowed to pass through our Earth's atmosphere. So why do you think that microwaves are suitable for mobile communication? Means all our mobile network communication works in this microwave region. So what does this have to do with the, or does this have something to do with the opacity or penetration tendency of a wave to the atmosphere, that it is suitable for communication? You just try to dig up, think over it, and then come up with the answer. Anyway, let's come to the next topic, and that is on plane waves. Now, I hope electromagnetic spectrum is clear to us. Means depending upon the omega value in this the expression for wave function for light waves, we can have a very vast spectrum. Now, what do we mean by plane waves? So basically, plane waves are the waves for which this amplitude A does not change with the distance as we go away from the source or from one point to other point in the space. This is not a function of r. So those waves are called plane waves. So plane waves means the waves which propagates from one point to another point of the space without any reduction in their amplitude. So from where we get the plane waves? So basically, ideally, they should be originating from, say, a plane surface which is emitting radiation, so that, okay, all the radiations coming from that surface are moving over a long distance, and then they lead to a simple plane. What do you mean by simple plane? I mean, okay, so for that we will need to understand about what is this wave front, so which is just coming after this. So plane waves are the plane for now. Let us just keep in mind that plane waves are the waves for which the amplitude does not change as we propagate along the space. Fine. Then second type of waves are spherical waves. What do we mean by spherical waves? The wave function for spherical waves is written like this. Now from here you should be able to make a difference. Spherical waves can be written like this. This component is similar. This exponential part is similar for both. The only main difference is this amplitude. So this is constant for plane waves. Here it is varying as 1 upon r. So if the variation of this component, this amplitude part, is 1 upon r, those waves are called spherical waves. Now you should ask a question, that why is this wave, this dependence why this dependence should be 1 upon r? Why not 1 upon r square, 1 upon r cube, or some other kind of dependence? So basically, this dependence is something which is required by what you can call conservation of energy. Now let us assume that we have a point source which is emitting radiation in all the directions. In that case, suppose that, okay, after certain time t, we just suppose we switched on the point source, source of light, and after some time t, the light from the source reaches travels a distance r and reaches at this point. Now since the light is being emitted in all the directions, all the energy which is emitted from this source, which was initially at just this point, now has been spread over the whole surface of this sphere. So because this is traveling in equally in all the directions with same speed, therefore this will be constituting a spherical surface. So the total energy is going to be the surface integral of the energy received at a small surface element. Let us suppose here is some small surface element where some amount of energy, say dE, is received. So total energy is nothing but sum of the energy received over all the points on the surface, and this sum, since surface is continuous, is actually going to be a surface integral. So that is your total energy. So we can say that, okay, the total energy is proportional to the area of the surface, isn't it? So means energy is proportional to 4 pi r square. And we know that intensity of radiation at a particular point is nothing but amount of energy received per unit area, right? Per unit time. So the intensity of radiation is given by this. So this is total area. So this is intensity. Fine. And we know that intensity is equal to, say, psi star psi, or amplitude star amplitude. That means this is complex conjugate of amplitude, and this is this. So intensity is related to this. We have done it, I think, in our previous classes. So means intensity should be proportional to 1 upon r square. So that if we find out amplitude from this, what should the amplitude be? Let me write down the amplitude is E naught. This is E naught here I'm writing. So this is proportional to 1 upon r. Suppose A is some constant of proportionality. So this is constant. A doesn't change, right? So for spherical wave, the conservation of energy demands that E is proportional to 1 upon r. Okay, now next let us talk about wavefronts. So basically the concept of wavefront is used to represent surfaces of constant phase for electromagnetic field. What is the meaning of this? Basically, let us assume that we have a stream of light waves which is traveling from left to right. So basically, suppose we have waves traveling from left to right. There is a beam of light traveling from left to right. So beam means it consists of so many light waves traveling along each other. Now let us assume we take snapshot of that beam at a particular moment of time. So what is shown in this figure is the snapshot of all the light beams, all the waves in the light beam which were traveling from left to right. And what does these values here tell us is, suppose the instantaneous value of the electric field. So here the electric field is maximum, here it is minimum. Please follow the cursor on the screen, right? So suppose here electric field is maximum. It is a snapshot of all the waves traveling in the beam taken at a particular instant of time. So we have frozen all the wave at a particular instant of time and then want to see the things. So here the electric field is maximum, it is lowest, it is highest, and so on. Now basically wavefront, that is what is the meaning of this sentence is, since they are normally used to show the spatial variation of the field, means now each of this line is now representing spatial variation of the electric field, means how is the electric field varying in the space. So at that particular instant of time, suppose where we have taken this snapshot, electric field is maximum here, it is lowest here, it is maximum, and since the wave is traveling, then this whole beam or whole wave may be traveling with the time. But now since we have frozen the time, so it is the distribution of electric field in the space taken at a particular point of time. Now what is the wavefront? So basically wavefront is telling you the locus of all those points in the space where the electric field is oscillating or is having same phase. So now you see, let us, if you go back to the definition of the phase, so this point, this point, this point, this point, this point, all these points are in same phase. So we can say this is the wavefront for this particular beam of light which is traveling from left to right. Similarly, these are not only the unique points which are having same phase. So let us suppose we chose the phase corresponding to the value where electric field is lowest. Then the same phase will be at this point as well. After 1 lambda wavelength, we will be having same phase. So means if there is one wavefront here, there will be another similar wavefront here. There will be similar wavefront here after a wavelength lambda. So this is what it means. So yeah, the wavefronts of the plane. Okay, the wavefronts can be plane, and this figure is coming up in the next slides. So another way of yeah, the field is periodic. Since the field is periodic, now you can see here the electric field is periodic. So the given value of phases will also result in multiple surfaces, as I told you. Okay, this is one surface. I can say this is one wavefront, second surface, this is second wavefront, third surface, this is third wavefront, and so on. So we can have so many wavefronts corresponding to a beam of light traveling along a particular direction. There is another way of defining wavefront. These surfaces are separate. Okay, these surfaces are separated by a wavelength lambda. So as I already told you, fine. Now there is another way of defining a wavefront. A given wavefront also represents a surface of constant optical path length from the source. Now this is something interesting. What do you mean? First of all, we need to know what is the meaning of optical path length. And then what is wavefront? A wavefront is the surface of constant optical path length. So optical path length follows from this. Optical path length, if you see this integral, it looks little very complicated. What is the physical meaning of this? So let us come to the physical meaning of this. And I think that meaning lies here. Now suppose we have a point source of light. And let us forget this blue color here for time being. So this is white, all whole white. So means once we switch on this source, what will happen if the space in all the directions is identical, means it's air everywhere? What will happen? The light will propagate with the same velocity in all the directions. And if we try to see that, okay, after some time t, where the light signal has reached, suppose it has traveled say a distance r along this direction. Now since the space all over is same, so the wavefront is going to be a sphere, correct, as we have discussed in our previous slide as well. Now let us assume that we have some different medium in this region. So suppose we have a liquid here which is having a refractive index. So n here in this integral refers to the refractive index of that particular path. Okay, of a particular path which is lying in between say source to point P, wherever we are wanting to find out the waveform or wavefront. So if this is an integral because you may have a path in between with varying index of refraction. If index of refraction is constant, then this can be taken outside. Then optical path length is just simply refractive index multiplied by the geometric path difference, so difference between S and P, distance between S and P. So in this figure, let us try to see, okay, so what is the geometric path difference? Say this is 0, this is R, so the geometric path difference is say R. Optical path difference, so here it is R because there is no medium, I mean it's a vacuum or air, so the optical path difference is also R towards this side because n is 1 for air, index of refraction is 1. Now if we try to see to this side, suppose it is a denser medium, let us say water or any other medium, then refractive index here is greater than 1, correct? If refractive index is greater than 1, then what do you think? The optical path length, if you come here, n is greater than 1, correct? So what will be the corresponding geometric distance which this light will be traveling in this direction? That is going to be slightly less. That is going to be slightly less. Means wavefront is locus of all those points which have same optical path difference, correct? So here light has traveled a distance r. Here it will be traveling little less distance because in a denser medium light travels slower. So the optical path difference is this much in that case. So constant. So what will be the locus of all the points with constant optical path difference? That is going to be something like this. Okay, this is going to be like this part of sphere to this region. Now in this region, this will be traveling little less distance along this direction, because n is larger than 1. Optical path length has to be same, correct? So now since we are multiplying it with the number which is larger, I hope I am able to convey it to you. So if you see this here, the n is 1 here, n is 1 in this direction, and n is larger than 1 in this direction. But for all those points, optical path difference should be the same. So in this case, optical path difference is r. To this region, optical path difference is r because n is 1, but here n is greater than 1. So corresponding geometric path difference should be lesser, so that the product of this thing, product of ns and ds should remain same. So if n is greater than 1, ds should be less. So means this geometric path difference, geometric path traveled by the light along this direction is going to be smaller. So means the wavefront in this case is going to be of this particular shape, maybe of this shape. So that is what is the definition. That is another way of defining what you call the wavefront. Means it is the locus of all the points for which the optical path difference from the source is the same. So I hope you understood the concept of optical path length. If you didn't get it, you can come back to me via comments. We can discuss it. So okay, there's another illustration of this optical path difference in this figure. So here, suppose this is a lens. This is optically denser body or optically denser object. We are putting on it a plane wave, and then what will happen as the plane waves are incident on the lens? What happens in this region? The light has to travel a very lesser portion of the denser medium. So what will happen? The light will enter into this medium, and after some time it will emit, and it will travel little faster here, because in denser medium it will be moving little slower. Now it will be moving little faster, right? So that is why we see, so in this region light will travel little extra path. So from here it is coming, the light which is coming from this point to this point, if we see this as a wavefront, plane wavefront, so light just enters here, then what will happen? It will travel this long path through this. If you see this wavefront, the light just emitting from here, corresponding lights have traveled a little extra path here, because this portions of the wavefront have to travel lesser denser medium. So that is how we can understand the concept of the wavefronts, right? So I hope it is clear to you. In case not, you should come to the discussions. We will discuss it. Okay. Now, depending upon this what is the source of the light, we may have a plane wavefront. Even if you see a spherical wavefront at a very large distances from the source, it will look like a plane wavefront. It is something similar to this. The earth actually is spherical in shape, but if you go to a particular point on, if we are on a particular point on the earth, we will see very large flat grounds on the earth, just because it is very big in size. So if it is very big in size, if we take a very small portion of this, it would look like a flat one. Same is the thing here. Okay? So means if you have a spherical waveform, and if we look it at a very large distance from the source, you will see, okay, it can roughly be taken like a plane waveform, right? So basically plane wavefronts can be taken as special case of spherical wavefront with r to be very large, means distance from the source is very large. I hope I'm talking of this r. So this is spherical wavefront. If r is very large, we are going very away from the source, then we can take a very small portion of this wavefront as a plane wave. That's okay. And that is spherical wavefront. This is originating from a point source. This is aberrated wavefront. Now this concept belongs to the optical path length. Suppose we have a plane wavefront which is traveling and is made to pass through a medium with varying index of refraction. And what will happen? Some portions of the wavefront will travel faster, some may travel little slower, and this wavefront will be aberrated. So this will be something like a aberrated wavefront. One thing which is very crucial to notice is that the distance between any two wavefronts will always be equal to the wavelength of the light, lambda. So that always remains the same. Now the next concept is of interference. Let's come to the interference now. So when two more okay we have studied in our vector analysis that okay, when more than one vector superpose with each other at some point in the space, the resultant can be written as the resultant can be written by the superposition principle. Now we are talking of electromagnetic waves, and those are the waves made up of electric fields and magnetic fields, and those fields are the vector quantities. So if you have more than one components of electric fields which are superposing with each other at point in the space, then the resultant electric field can be written as the vector sum of all the uh, components of the electric fields. So that is what defines the resultant of electric field, and this is the basic principle behind the interference principle. So interference phenomena is coming out of superposition principle. So this is superposition principle, means if you have two electric field, two waves represented by say electric field E1 and E2. If you say 2, if you have more than 2, then this will be actually sum over all the waves which are coming from different regions of the space to a particular point. So interference in general is it is a general phenomena which can take place because of more than two waves. Usually in textbooks we see only two waves, which are just illustration of basic principle behind interference. In reality, there may be so many waves coming to a particular point and interfere with each other. So the resultant is just going to be given by this equation. And intensity, what is intensity? The resultant intensity will be the time average of the modulus squared of the total complex amplitude. So this is complex amplitude. And it is the one which is appearing in this equation. So complex amplitude, let me quickly, okay, this is what we call the complex amplitude. This is what is the complex amplitude. So intensity is actually given by the this modulus squared, the time average of this modulus square of the complex amplitude. It's just like a star A, means complex conjugate of amplitude times the amplitude itself. Intensity is given by the product of the two. Now suppose that two light waves, now let us limit ourselves to simple case of two light waves only, which are represented by say electric field E1 and E2. They superpose with each other in some region of the space. In that case, the resultant intensity will be given by, so this summation now is restricted to just two terms, E1 and E2. So in that case, intensity is given by this, because this is a vector quantity, so this will be E1, E will be equal to E1 plus E2. So intensity is E square, means square of left hand side thing. So this will be E1 square plus E2 square plus E1 E2 star E1 star E2. So this is for vectors. This is how square is taken for the vectors. So the intensity is given by this. Now we can write down the intensity using this. So this is nothing but E1 square, intensity of the first intensity associated with the first wave, intensity associated with the second wave, E2 square, and this is the term, these two terms are the terms which are going to be responsible for the interference phenomena. Now taking a simple case of linearly polarized light, let us assume we have a linearly polarized light. Now I hope you have done it somewhere in your lower classes. If not, let me quickly tell you what is the meaning of polarized light. So linearly polarized light means the oscillation of electric field vector is restricted to a particular direction. It doesn't change. Suppose that electric field vector is oscillating in x direction, so it will always be oscillating in x direction. That type of light is called linearly polarized light. And there can be other forms of polarization. You may have a circularly polarized light. In that case, the electric field vector keeps on oscillating in xy plane, so that is called circularly polarized light. So polarization we will be doing maybe somewhere later. So linearly polarized light. Okay, so simple linearly polarized light means this component amplitude ai is restricted to a particular axis. It has now here we are talking of omega I, not omega, means we are not talking of monochromatic light. So interference is not necessarily the game of say monochromatic radiation. In your classes you have been told that okay, for obtaining interference fringes or pattern, you have to have sources of light which are monochromatic and which are in fact derived from a single source. What are those sources called? Okay, you let me know in your comments. So they should be coherent sources, right? So coherent sources. So now that is a special case. In general, even if you have light waves with two different frequencies, interference can happen, superposition can happen, because this is a basic fundamental property. So that is why we are saying okay, if we have two different waves of even different frequencies and both are having their different phases, even then the resultant is going to be given by this expression. I will be say I1 I2 the same thing to A1 dot A2. So because for first wave it is A1, second wave it will be A2. And what will this give you? I hope you have studied those Euler identities, exponential functions. Cos of theta is equal to e raised to the power iota theta plus e raised to minus iota theta upon 2, that kind of identity. So if we use those identities, we can write down E1 plus E2 will lead you to this. I mean intensity will be this one. So I mean we are putting E1 E2 values here. Fine. So finally we will be getting this cos of omega 1 minus omega 2. I leave this expression to you for simplification. You try it as a homework. So this will be cos of omega 1 minus omega 2 into t phi 1. So this is coming for first one minus phi 2. So the intensity. So there are two important things which we should notice here. These are two terms, A1, A2. These are related to the polarization, linearly polarized light. Now suppose there are two lights which are uh, superposing in a region, and one of the light is polarized in x direction, x polarized, and second one is polarized in y direction. In that case, those A1 and A2 will be perpendicular to each other. In that case, there will not be any interference effect. So, means for seeing the interference effect, the polarization of the lights must not be orthogonally, the two light waves must not be orthogonally polarized to each other. Orthogonally polarized means the direction of polarization of the lights is perpendicular to each other. In case they are orthogonally polarized, this term will be 0. So everything appearing here will go to 0. So the intensity is just I1 plus I2. So we won't be seeing those maxima and minima pattern because of interference. So one very basic requirement is they should be polarized in the same plane. If they are orthogonally polarized, we won't be seeing the interference effects. Second is this omega 1 minus omega 2. Omega 1 minus omega 2. So means if the two are having different frequencies, means temporal frequencies are different, what will happen? We will be seeing beats. I hope you have done, we have done it in our previous classes. When two waves of slightly different frequencies superpose, what they produce are beats. And beat frequency is given by omega 1 minus omega 2. So basically in that case, Okay, even if A1 and A2 are not orthogonal to each other, means they are linearly polarized in same plane even, and but their frequencies are not same, means their the omega 1 and omega 2 are not same, they are slightly different. Then we will find out, okay, there will be interference pattern, but what we will be finding is that at some time it will be having a maxima, then it will be going down to minima, means there will be a beat, time dependent beats. So that is why to obtain the stable interference pattern we must have omega 1 equal to omega 2, if we have to obtain stable pattern which is independent of time. So omega 1 and omega 2 must be the same. That is why we say, okay, we should have monochromatic source of light. Two sources of light must be monochromatic to obtain interference pattern. uh, okay, so this expression actually is the general one. This applies to any situation. Now let us come back to the interference fringes and limit ourselves to the special case. And the special case is that, okay, we are using two linearly polarized light which has parallel planes of polarization. Now you know what are parallel planes of polarization, and the two waves are having same optical frequency. Suppose omega 1 is omega 2. In that case, the expression for intensity turns out to be this one. I hope you can find it out very easily. Put there omega 1 is equal to omega 2. Then we will be finding from here a1 a2. You know what is a1 a2? This relates to under root of I1. A1 is under root of I1. Similarly, we can find out, we can write down this. So delta phi is the difference in phases, phi 2 minus phi 1. So this is the intensity in that special case. Okay, if we try to plot this intensity, then this intensity as a function of phase difference. Now remember, it's not interference pattern. We are just trying to plot this intensity as a function of this phase difference between the two waves. And as a function of phase difference, you can find out there will be a maxima when this is just 1, because this is a cos function. It can run between plus 1 and minus 1. So if it is plus 1, you will be having maxima. If it is minus 1, you will be having minima. So that is how, with the different phase difference, you can find out this kind of pattern, and this pattern is one which leads to the interference pattern which we see on the screen. So this is not something which we see on the screen, it is just what is the change in intensity with respect to phase difference between the two waves. Now actually, to see what is happening on screen, we have to look at path difference. I hope you have done that in your maybe lower classes. So basically, yeah, so for constructive interference or for seeing a bright fringe, the path difference, sorry, phase difference should be 2 pi m. So this phase difference between the two waves must be 2 pi m. And if you have to see a dark fringe or minima, then the phase difference should be 2m plus 1 times pi. So this is the same simple cos function property, and you can see it from here. And in terms of path difference, actually in our lower classes we used to find out the path difference. So that path difference is not important. It is actually the optical path difference which is important. So we have defined in the previous slide what is optical path difference. So for constructive interference or for seeing a bright fringe, the optical path difference should be integral multiple of the wavelength. And for destructive interference, it must be half integral multiple of the wavelength. So this is the condition for interference pattern. Here M, I hope you're seeing here M. Oh, M appearing here is called order of interference. So first order, second order, third order interference, and so on. Well, so yes, I think I have already defined this. Optical path difference is just optical path difference for first wave, optical path difference for second wave, and the difference between them is called optical path difference. So this is optical path length, not path difference, sorry. This is optical path length for first wave, this is optical path length for second wave. The difference between them is called optical path difference. So this is lambda upon 2 pi times the phase difference. Obviously we can calculate it so that we can find out the phase difference is equal to 2 pi by lambda into optical path difference. Right, so we will be seeing that interference pattern in many examples to come. So this is a general theory of interference. So now let us first talk about the some basic parameters which characterizes the fringes which comes out of interference. So one parameter is called fringe visibility. So to define what is fringe visibility, let us write down that expression for total intensity, which is coming because of superposition of two monochromatic waves which are linearly polarized, and their plane of polarization is same. Or say in that case, let us write down, say I naught is equal to I1 plus I2. This is just sum of intensity of first and intensity of second source. In that case, I can write down I is equal to I naught into 1. So I have taken this common. So this is 1. 1 refers to I1 plus I2, which is sitting here, and gamma. So I have defined one new term called gamma here, where gamma is equal to, you can simplify this expression, and gamma is equal to nothing but 2 times I1 I2, 2 times I1 I2, because cos factor is as such coming downwards. So gamma is I1 I2 under root this 2 into I1 I2 under root divided by I1 plus I2. So this gamma is called the fringe visibility. This is called fringe visibility. So this is also, we can relate it to the quality of the fringes, right? There is another way of defining gamma, the fringe visibility, and this is equal to I max minus I min divided by I max plus I min. Now you should ask a question: how are these two expressions equivalent, right? So you know what is I max? I max is related to I1. I min, oh sorry, I max and I min, maximum and minimum intensity. Sorry, I max and I min are coming from here. Okay, this is your I max, maximum intensity. This is your I min, right? If you use these two expressions and put them in this equation, then you should find out gamma turns out to be nothing but equal to this one. You do it as a homework. So this fringe visibility can be defined as intensity of the maximum fringe, maximum intensity of the interference fringes, minus minimum, means this is bright fringe, intensity of the bright fringe minus intensity of dark fringe, divided by the sum of the two. So this is called fringe visibility. So basically, if dark fringes are perfectly dark and bright fringes are very bright, then fringe visibility is going to be what? This I max will be equal to, say, 1. I min is 0 in that case, means the dark fringes are totally dark. Let us say this is 1. In that case, fringe visibility will be 1. So for ideal fringes, you should find out the fringe visibility is 1. So I think that's all for today. Please go through this lecture carefully and let me know your questions in the comments, and if there are any doubts, I will be happy to answer. And next class we will be continuing this further to understand interference in more detail with the help of certain experiments on interference. We will discuss certain experiments on interference. Till then, thank you very much. Stay home, stay safe.